So it's 6:05. I'll start. If other wants to join, they can join. So I welcome you to.
Yeah, please tell.
Yeah, I welcome you to the first problem solving session of the NPTEL course Combinatorics. So the
Yeah.
for yeah, so the format of the session is I will be solving few problems from the topics covered during the week, and you like if you have any doubt during the problem solving, uh, you can unmute yourself and ask your
Right.
questions, like so
Yeah.
so I'll start. So first of all, I'll recall the principles that were discussed during this week. First was pigeonhole principle. So it said that if you have k plus 1 objects and you have to put k plus 1 objects in k container, then at least one container will have two or more objects. Then we have a stronger pigeonhole principle, which said if there are n1 plus n2 till nk minus k plus 1 objects, and same you have to put them in k boxes, then there exists at least one ith box which will have ni objects or more than ni objects. So first of all, I have few remarks regarding the pigeonhole principle. So first of all, we can see that this n1 plus n2 plus nk minus k plus 1 is the minimum number that is satisfying the condition, that is satisfying the condition that first box will have n1 objects or more, or second box will have n2 objects, and so on. This is clear, right? Because if we take, so we have to show that this is the minimum number satisfying this condition. So we have to show that any numbers the number closest to it and smaller than it, which is n1 plus n2 plus nk minus k, does not satisfy this condition. So if we take these many objects, this star condition need not be satisfied, because be satisfied because we can put n1 minus 1 basically ni minus 1 objects in ith box. So we see that strong pigeonhole principle is giving us two things. First it is saying that if we want to put n1 plus n2 plus nk minus k plus 1 objects in k boxes, then we'll have at least one box, ith box, such that that box will have ni or more than ni objects, and this number that we are getting, n1 till nk minus k plus 1, is minimum such number which is satisfying this condition. And second remark for strong PHP is this, that if we take ni equal to 2 for all I, we retrieve our basic pigeonhole principle. And the third theorem that was covered was Ramsey's theorem, which says that, so we for some sorry So Ramsey's theorem says for bunch of integers n1 nk, Ramsey number exists. So what is the Ramsey's number? It says that if we have k colors c1 till ck, if c1 till ck, and if Ramsey number for n1 till nk is p, it just says that we can every every kp color, if we take a kp complete graph with p vertices, and if we take k colorings with these many colors, then we'll in that kp either we'll have a c1 colored kn1 or a c2 colored kn2 or ck colored knk. So, and besides these, you covered various applications of pigeonhole principle. Now we'll solve some problems relating to it. So our first problem is, our set M is consisting of n positive integers. Say M is equal to x1, x2 and xn. And we have that none of these numbers have a prime divisors larger than 6. So xi has own prime factors. What are all the possible prime factors? 2, 3 and 5. Then the claim is that M has two distinct elements whose product is a perfect square of integers. And we have to find the least n for which this property is holding. So first of all, now since each of xi's are positive integers and they all have prime factors 2, 3, 5, so we can write each xi's as basically 2 raised to the power ai, 3 raised to the power bi and 5 raised to the power ci, where ai, bi and ci, they are powers of 2, 3 and 5 respectively for each xi. Now, what do we want? We want to guarantee that for this n, we can always find two integers xi, xj such that xi, xj, their product is a perfect square of integers. Is a perfect square of integer. This is same thing as saying xi, xj. Now what will be xi, xj? It will be just 2 raised to the power ai plus aj, because ai was power of 2 in xi, aj was power of 2 in xj. So this will be 2 bi plus bj, 3 raised to the power bi plus bj and 5 raised to the power ci plus cj. Now we want that this is a perfect square. Square of an integer. And now when is a number a perfect square? When it has some
Even powers.
when it is a power of some square. So in this case, when this will happen, when we have ai plus aj, bi plus bj and ci plus cj, this is even. This can only happen only when these powers are even, because then our xi, xj will be 2 ai plus aj by 2, 3 bi plus bj, 3 raised to the power bi plus bj by 2, 5 raised to the power ci plus cj 2 whole square. And all these numbers, since because ai, aj plus aj is even, bi plus bj is even.
One second. I just will call, I'll reply. Just one
ci
second.
plus cj is even. Therefore, this is a Therefore, this is a power of some square. So we were now. So this is a power of. So now this when is this satisfied? So I'll request you to mute yourself if you don't have any doubt. Now, when is this property satisfied, that all these sums are even? We want that ai. So basically, sum of two integers x plus y is even if and only if both xy are odd or both xy are even. Now, so so to so we want to guarantee, therefore we want to guarantee that from our collection of n integers, we can always find xi xj such that ai aj have same parity. By parity I mean either they are both odd or even. Bi bj have same parity and ci cj have same parity. So now we want this. So our xi was 2 raised to the power ai, 3 raised to the power bi, 5 raised to the power ci, and xj was and our xj was 2 raised to the power aj, 3 raised to the power bj, and 5 raised to the power cj. So we want from our collection we want two integers such that ai aj have same parity, bi bj have same parity, and ci cj have same parity. So combinations or possibilities for ai bi and ci, they can either be all odd. Possible combination for powers of 2, 3 and 5. They can all be odd. One can be odd, both even, and so on. So how many cases are there? Each power has two options, either odd or even. So we have total 8 combinations. Now we have that we want product of xi and xj to be a perfect square. From any collection we want two integers such that their product is a perfect square, and this can only happen when ai aj have same parity, bi bj have same parity, ci cj. So basically these two so we should guarantee that from our collection two of the integers will lie in the same boxes. So these are our sorry, okay. Oh, sorry. for powers of 2, 3 and 5. So now for our problem, we want so we have 8 boxes and we want 2 integers to go in the same box. Therefore, least n should be 9. Because if we have 9 integers, at least 2 of them will go in the same box. That is, at least 2 powers of 2, 3 and 5. For 2 of them will have same parity, which will make them that the product is even. So is the first question clear to everyone?
Yeah, it's clear.
Okay. So now we move on to our next question. So our next question is,
Excuse me, these PDFs will be available after the class?
Yes. These lectures are recorded also, so you can watch them later also.
Okay.
So, yeah. So question 2 is, so we have to find the minimum number of students, each of whom so we have some students which are coming from 28 states and 8 union territories. So now we have to find the minimum number of students that can be enrolled in a university, so that we can guarantee that there are greater than 100 students who are coming from the same state or same union territory. So we want at least 100 student coming from the same state. So now can you guess what can be our boxes and what can be our objects?
These are states and union territories are the boxes.
Very good. So we see that states and union territories are our boxes. So how many boxes are there? We have 28 plus
36
boxes. And what are the objects? Objects are student, and we want greater than equal to 100 student in at least one box. So what should we do?
36001.
Okay. But we need to find the minimum number. Are you sure no number less than 36001 will work? Is 360...
Yeah, but simultaneously it will not confirm also.
It will confirm. So see, we can see.
It should be 36 into 99 plus 1.
Why?
You can assume 99 in each of them, and then there is one person.
Yes.
Which will make it 100.
Yes. Very good. So either you can look at like this, or you can look at like this is what he is using. He is using the strong pigeonhole principle. So our strong pigeonhole principle I discussed in the beginning. Strong pigeonhole principle give us the minimum number. So we have our box. So we have our boxes. So we have 36 boxes, and we can, so our ni's is equal to 100 for all I going from 1 to 36. So from strong pigeonhole principle, the number will be 100 plus this added 36 times minus the number of boxes, which is 36 plus 1, which is same as 36 into 99 plus 1. So now why we are saying this? Because see, when you are doing 36001, this number 36 into 99 by 1, this will come out to be
101. That comes. In that case, 101 actually. I thought 101 instead of 100.
Yeah. Okay. Yeah. So this is 3565. So this question is clear to everyone? So why the answer is 3565? Okay.
Yeah, clear, clear.
Our next question. So now, yeah. So we have this. Now we have to determine the minimum integers to be selected from the set 1 till 29 such that at least one pair of these numbers add up to 30. So first of all, so we want at least one pair of these number add up to 30. So this is also a pigeonhole principle problem. So what should be our boxes? We want two numbers which should add up to be 30. So first we'll
We
see.
can collect all those numbers which can make the summation as 30, like 129,
129.
327, this 327, all these.
Yes.
And from there we'll select 111.
Yeah.
The moment we select one more other than this, how many boxes we can make? One more extra we select, it becomes this.
Yes, very good. Yes, so this is right. So first we see what are the boxes. So we have all the possible this. So we'll see 1, 3, 5, 27. So what we have these combinations. We can go till 13, 13, 27
17.
and sorry 17 and 15. So we see we have 1, 3, 5, 1, 3, 5, 7, 9, 11, 13, 15. We have 8 boxes. So
9 is ours.
if n is 9, then by pigeonhole principle, at least 2 will be in same box and we are done. Since because we are choosing 2 and we are choosing distinct integers, we won't end up in this box. Hence there is no problem. We'll end up in either. So more than 2 elements will lie either in this box or this box or this box. So we are fine. Now next question. So next is some easy examples of Ramsey's theorem. So first one is very simple. So this is just to see the application of definitions. So what is R2n? We want to find least p such that Kp, which is the complete graph over p vertices, such that Kp has, and we are choosing two colors. Suppose first color is red and second color is blue. So R2n is the least p such that Kp has an edge of red color. Why edge? Because K2 is an edge. K2 is a complete graph on two vertices, which is just an edge. Or we want a Kn of blue color. So is it obvious why R2n should be n? First of all, since we are saying that it's the least p, first we see if n minus 1 works. So if we take Kn minus 1 with all vertices, with all edges of blue color, we see we cannot have an edge of red color, or neither we won't have K2 of red color because there is no edge of red color. Also, we won't have Kn of blue color. We have, because vertices are 9, vertices are n minus 1. So we cannot have a complete graph of n vertices inside a complete graph of n minus 1 vertices. So we see that n minus 1 doesn't work. Therefore, R2n, we see from this, has to be greater than n minus 1. Now we see why R2n is equal to n. So if we take Kp, Kn, suppose we have, okay, so we have to show, okay, so, to show we have either Kn of blue color or K2 of red color. So if we have to show or, so it is sufficient to assume that one is not there and to show the other is there. So suppose we don't have Kn of blue color. This means at least one edge of Kn is red, which means that we have K2 of red color. Now this was easy, this was R2n. So is it clear? Okay. Now B part is R33 is 6. So this was done in class, done in the lectures. So if you have any doubts, we can discuss. Otherwise, we can skip it and go to the third part. Okay. So now C is R3 3 is less than equal to 17. So we have to show that this is less than equal to 17. So basically what we have to do to show K17. So if we color K17 with 3 colors, red, blue, green, then K17, okay, any 3 coloring of K17 will either have red triangle or blue triangle or green triangle. So we will be using the previous part for it, which says that any 6. So if we have 2 coloring of any case 6, we'll have either a triangle of first color or a triangle of second color. Why are we saying triangle? Because on 3 vertices, complete graph is just the triangle. Now to show this, let's pick V1, one of the vertices. Now number of remaining vertices is 16, plus we have 3 colors. So from pigeonhole principle, we see that we'll have vertices, we'll have at least, so we have remaining vertices is 16, and therefore the remaining edges from V1 so remaining edges from V1 to Vj, they are also 16. So from pigeonhole principle we see that we'll have at least 6 vertices. Let's name them V2 till V7, such that V1 V2 till V1 V7 they are of same color. Same color, say red. Now two cases can happen. Case 1, there exists at least one edge V1 Vj, where j is then 2 to 7, which is red. Then we are done, because our triangle will be just V1 Vj. There exists at least one edge with this. There exists at least one edge V2 Vj. Sorry, I mean there exists at least one edge Vi Vj where Ij belongs to 2 to 7. So we are considering these vertices only. First case is that. So if we get this, then our triangle is basically V1 Vj. We are done because our triangle is just V1 Vi Vj. And case 2 is none of the Vi Vj where Ij belongs to 2 to 7, 2 till 7 is red. Therefore we see that this gives case 6 of vertices V2 till V7 of the other two colors, which are this. Then from part B, we'll have a K3 of blue color or a K3 of green color. So we have shown that 17 works. Therefore Ramsey number of 333 is less than equal to 17. You can check. It is actually 17. That is, find a 3 coloring of K16 with no triangle of same color. Is this fine?
Yeah, we can move to next floor.
Yeah, okay. Now, our last question is, given any 52 integers, there exist two integers whose sum or difference is divisible by 100. So any ideas how to do this? So we have 52 integers and we have to show there will be at least two integers whose sum or difference is divisible by 100. So we want to find two integers x, y from collection of 52 integers such that x minus y is divisible by 11. Okay.
11 or 100?
100, sorry, yeah. Somebody entered, so I got. Yeah. X minus y is equal to 100k or x plus y equal to 100k k dash. This can happen like difference of two integers is a multiple of 100, or sum of two integers is a multiple of 100. This can happen only when remainders of x and y when divided by 100 are same. If they are same, then their difference is a multiple of 100, or they add up to 100. If the remainders add up to 100, their sum will be the multiple of 100. So now we want to choose our boxes. Now we want to choose, so for pigeonhole principle, we want to choose our boxes in such a manner that two integers always end up in a box so that there's sum of remainders is 100, or they have same remainders. So our set of remainders is 1, 2 till 99 and 0. Now we want to choose our boxes in such a manner that their sum is 100 or they are same. So we take our boxes to be these: 199, 298 till 49. Sorry, yes, this is fine. So 49, 51 or 0 or 50. So we see we have in total 51 boxes and 52, sorry, but integers are 52 So we are done by pigeonhole principle. This question was fairly easy too, right?
Yeah.
Okay. So okay, now now we can discuss if you have any doubts, like from the lectures, or if you want to discuss anything related to the course lectures or any doubts in the courses.
I was just going